first lecture we saw, can you give me the mic? Okay? Can you hear me? No, the shout. Okay. So we saw that from Coulomb's law, we started with charges, force, Q1, Q2, R equal to use this, take on the force on 2, equal 1 is Q1, Q2, so 4, 5, epsilon R squared. Directed force of Q, if Q1, Q2 are positive, is repulsion, Q1, Q2 negative, repulsion, Q plus minus attraction. And then we saw that from the idea of force, you can go to the idea of field. You have to E. E is defined as force over Q, charge. In this case here, we take Q2, Q1, R, at this point here, we show the plus 1. So Q2 is equal to 1. This is giving P. Here, that is P. This is called the test charge, unit positive test charge. That's what we said. So you can see this definition is very convenient. Very convenient. If you want to find the field at a given point, you just find the force acting on the unit test charge there. Whatever complicated distribution of charges, doesn't matter, you just find the force. So this is very at the beginning. But certain bodies have got symmetry. When you have symmetry, using this method can be quite messy, quite cumbersome, very difficult, very messy. So the best is we look at the symmetry, we look at the whole distribution of charges. For example, if you have a sphere, spherical sphere of charges, the uniform charges here is spherical, so here is A, then you want to find the field at the point P, distance of R from the center, then we say use the idea of flux. According to Gauss's law, the integral of d dot ds, I'll write down ds, small element here, ds vector, is equal to net q enclosed. So the charge is net q enclosed. Enclosed surface, gs is the Gaussian surface, so here they say Gaussian. The Gaussian surface must always pass to the point where you want the field to be. Okay? So the net q enclosed here, net q enclosed is q, okay, that's q. This one, d dot ds vector, we saw already, it actually means d normal times ds. Normal component of d times scalar ds, because this is vector. Because the unit vector, a vector ds, as we said before, is defined as scalar vector x ds with a label. This is very standard. So when you multiply this by this, you get integral over the Gaussian surface here, this surface here, gs Gaussian surface. Is equal to net charge. So the Gaussian surface was closed, cannot be open. Closed. So you can see this particular case. So we go to this. The mode of charge is uniform, is the symmetry. If I take a point here, P, P1, P2, P3, P4, and so on, and I keep the distance R the same, what will happen is that the value of the field component of D normal to the surface will be the same, but of course it's going in different direction. It doesn't matter. We show you what is scalar. So here is called scalar dr, which I'm looking for. Multiply by, since it is the same, this dr is independent of the surface area. It is 4 pi r squared is equal to q. So therefore, I have dr is q over 4 pi r squared. Have you obtained d, the displacement vector, displacement quantity, dr is related with dr to epsilon. So therefore, I get my dr is dr epsilon is q over 4 pi epsilon r. So therefore, the electric field or the ER is going this way, and I've calculated this way. But you can see how difficult it would have been if I have to use the original method. I want to field at point P, I put the unit test charge there, and I chop this small element, and I find all the contribution from all these volumes of charges, and add them together, add, subtract, sum them together, and that will be field. But not necessary to do this because you can see this charge has got symmetry, spherical symmetry. So whenever bodies of charges have a symmetry, obvious symmetry, I don't use the original method of +1, and also I find flux, the idea of flux. So the idea of flux, net flux, electric flux, is the same as charge. So what we did here, net flux is flux. Net Q enclosed is the net flux. It's a net flux. Net flux, net charge. So this allows me to calculate electric field another way, but of course when you have symmetry. We can do the same thing for simple distribution of charges. For instance, if I have a point charge, which you know the answer already, you know the answer of the point charge that is, calculate the electric field at point P, distance R from the point charge. Of course you know the answer. The answer is Q over 4 pi epsilon r squared. This is the electric field. But suppose now we use Gauss's law using symmetry. Simple, that's simple. So, this point charge is a sphere, is like a spherical symmetry. A point is a sphere of small radius. So as a spherical symmetry, therefore I use Gauss's law, flux. I want to feel the point P, this is an R. I must make sure that I draw the Gaussian surface which is closed, has the same shape, same geometry as the point charge. So therefore I draw a sphere. Over the sphere, the field will be absolutely will be normal, D will be normal. At the same distance R, the value of D is the same, although the point in different direction. I will move around, but it doesn't matter. We want the flux normal, multiplied by the area, so dr times 4 pi r squared is equal to Q. How do you know already, right? You know the answer will be what? So in this particular case, we know the surface. So I have put one charge. I have some comments here. The net flux coming out is d dot ds, normal component, which have a radius dr 4 pi r squared, and then charge is q, and then find d, dr, is radial, and find er. So this is Gauss's law, and give you inverse law, as you know. So therefore, as I mentioned before, using Gauss's law helps a lot. Makes life much easier. So significance of Gauss's law always valid. Even the Q is changing with time, doesn't matter, still valid, except that the charges have to change with time. So that doesn't matter for that being. So look for symmetry. We're looking for calculate the electric field coming out from an infinite line charge. Very long. The charge per meter is lambda coulomb per meter. I want to find at the distance of R, at the point P, for example, what is the value of the field. So you can see that, again, a line charge is like a cylinder or small radius, so therefore it's very long. Therefore, my Gaussian surface I choose to calculate the field passing the point P must have the same geometry, same shape, cylinder. This is also cylinder. This is cylinder or small radius. This is cylinder. What? Gauss Gauss's law says the net flux out of a closed surface. You draw a cylinder, the cylinder cannot be opened, the cylinder is closed on top, closed on the bottom, and you have a closed surface here. These are the model here. The line charge going to here, infinity. I'm picking a cylinder here like this, radius of r. Here, the surface is this way, normal with the line charge. Take this normal line charge, take this parallel line charge. So according to Gauss's law, I must sum all the electric flux coming out of the surface. Outward flux is positive, inward flux is negative, but the charge is positively positive, therefore all the flux are positive. So, contribution comes from the top. With the top I got no contribution because the electric field is, by symmetry, is not parallel to the surface. The surface on top is electric field parallel. Here. The parallel vector, by symmetry here, I got zero normal component. Gauss's law talks about the outward normal flux, and no flux normal to the surface. Here, the no flux normal to it is parallel. So, contribution 0. And the bottom, again, the flux is parallel to the surface, along the surface is 0. What is left is the outside. So, here the flux is normal to the curved surface. Okay. So, at the given distance of r, expect dr for the same value. Therefore, the flux coming out of the curved surface will be dr multiplied by area of surface of the cylinder. The area surface of cylinder, very easy to find out. It's as if take a scissor, you cut the cylinder up, open it up. When you open it up, this is 2 pi r. This is the length is L. Therefore, the area is 2 pi r times L. So therefore, the net flux is dr times 2 pi r times L. Therefore, this problem, if you use Gauss's law, very straightforward, very simple to calculate. Okay, so therefore, we find that this is equated to the net charge enclosed. The net charge enclosed by the Gaussian surface is the length L times lambda coulombs per meter enclosed times L meter lambda L. So this equates to lambda L. Next page. Therefore, the answer is independent. Here, lambda by 2 pi r, function of L cancel out. So therefore, it means that this line charge, so long as it is very long, it will be long. Anywhere along the parallel to the line at the distance r, the field is the same. When you go round, it's because of symmetry. Okay? Now, if the line charge were not infinitely long, was finite, like this pointer here, laser pointer here, like this charge of lambda, I can't use this method. I can't use this method because if there is no symmetry, even in the axis, how it works. Because this cylinder, you can draw it anywhere you want on the line charge, the same. The field is the same. But if the line charge is finite, and I draw a Gaussian surface, I'll move the Gaussian surface out of the line charge, field will not be the same. The situation will change. So therefore, you can see Gauss's law, although it's very powerful, it can only solve problems of high symmetry. But it doesn't mean it's not valid. It is always valid, but you will not be able to use it to get an answer very quickly. Okay? Now, suppose we say, oh, why don't we use the original method? You can see the original method. Original method, I want to fill at point P. I want to fill at point P. I say, no problem. Okay, I'll point P here. Let me go to the diagram the other way. Infinite charge. I want to fill at point P. According to the old method, it doesn't look at symmetry. I put a charge of +1 here. I take a small element dl lambda, so therefore dq is lambda. lambda dl. Therefore now I go as usual. The force acting on this one here, positive, positive, repel. So therefore dE at P is equal to lambda dl times 1 over 4 pi epsilon naught epsilon, epsilon in general, times distance. This distance we say is, I don't know, L, small l, so it will be r squared plus L squared. Okay? Okay, 4 pi epsilon, no 4 pi, 4 pi epsilon r squared, this is r squared. This distance here. This is r, this is L, this is r squared plus L squared. Square root, square. Square root, square, you get the same answer. You are going to answer your thinking aloud. You didn't finish. R squared plus L squared, not R squared. Okay, but when you can see now, unless we are smart, we smartly take into account symmetry, you can see the field as you move at the point P, at the point P remain fixed, at the DL moves around, vector keep going into it. Very difficult. But if I'm smart enough, I use the vector here, which is DL again, and the distance, same distance here. So you can see I have this. If I resolve, the vector parallel to the line charge will cancel, provided these two distances are the same, therefore the resultant will be perpendicular to the line charge. So some is said by symmetry. Therefore, this method will involve integrating from minus infinity to plus infinity, but finally, after a lot of work, you find out that the answer is ER is Q as lambda upon lambda upon 2 pi epsilon r. So you started with r squared, but after doing integration, it has to be r. Provided line charge is fully. So it is something that always happens. For a cylindrical symmetry, electric field is not 1 over r squared, it's 1 over r. Which you have seen already. Just now we proved already when did this method using Gauss's law. Those of you who want the challenge can try this. Integrate this from minus infinity to plus infinity. As L goes to minus infinity to plus infinity, you should be getting the answer. Lambda plus 2 pi epsilon r. Okay, so I leave it to you. Now, let's look now at a case where you have something involved infinity. Where something infinite, you always have some kind of symmetry. Now we're looking at the field coming out for an infinite sheet of charges. Sheet, S-H-E-E-T. Oh, S-H-E-E-T. Sheet of charge. Infinite sheet of charge. The charge, the electric field is charged on both sides. Okay. So it is given by sigma coulombs per meter. The charges equal both sides. For example, the sheet is so thin that the sigma coulomb per meter equal both sides. Okay. So therefore, you can see this is goes to infinity, infinity, infinity. Therefore, you agree with me that because of the symmetry of the situation, electric field will be 90 degrees up, 90 degrees down throughout the whole space. So therefore, the symmetry, you cannot go like that because the whole thing is infinite. So it appears to be 90 degrees. So 90 will go up. This is positive charges, and the negative charge at infinity, positive charges and negative charge at infinity. Therefore, you have this geometry here. For simplicity, let me use a Gaussian surface, which is cylindrical. Or if I don't want it, I can use it, which is a cube. Doesn't matter. So now I apply Gauss's law. It's a closed surface again. Closed surface either this or this surface. This area is given by small area here. So this Gaussian surface has got 1, 2, 3 surfaces before. The top, bottom, because the symmetry of the sheet of charge, as I said before, electric field will all be 90 degrees of the charge. So therefore, electric field will be 90 degrees to the top surface now, different from just now. But electric field now will be parallel to the curved surface here. Parallel. So therefore now, the contribution will come from top surface, bottom surface, and nothing from the side. Because from the side, electric field in red is parallel to the surface. The vector which is parallel to the surface, I got zero component. So therefore the outward flux is zero. Here the outward flux coming out is zero, we expect that. Here it is D times area, bottom D times area. But watch out. A flux, Gauss's law is not the field theorem, it is the Gauss's flux theorem. So the flux coming out here of surface is going up. So the D times area. By symmetry, the same thing is D, but the D is pointing downward because this is positive charge. So this flux points downward, D times A. So therefore the total flux is D times A plus D times A. So the sigma times A, therefore the answer is D is sigma over A, therefore E is D over 6 epsilon, in general epsilon. Now, so I cannot stop telling you that Gauss's law is not a field theorem, it is a flux theorem. Look at the picture again. This Gaussian surface is a cylinder, or could be a cube, doesn't matter. The top, the D is pointing up positive Y, say. But the D at the bottom is pointing negative Y. But Gauss's law doesn't talk about field, Gauss's law talks about flux. Pressure too high. It's better than it goes, no? Otherwise, bad for his pump can handle the problem. No good. Better it goes. Leave the pressure. So you can see, so the top surface, the flux coming out is positive, D times A. The bottom surface, the flux coming out downward, D times A. But it is not dA minus D. No minus here, because Gauss's law says the integral of the normal component of D, outward flux positive, equal to natural activity. So here you can see a classic example. This electric field going up, coming down, but the flux are all the same sign as IGL. So we'll look at another example to show you how the sign will be taken into account for the flux. So we take the flux normal to be positive, as a convention, just like unit normal to be zero. Okay? Now let's look at another illustration of this. Now, what we see is that if we have a sheet of charge of current density sigma coulomb per meter square, I'm able to kind of field. So that is why if you have wow, so fast. Huh? You're going to talk there, or you're fast. You're a marathon runner. I think that is so fast. You're very fit. Anyway, okay. You're very fit. Just now, I said something that the flux coming out here positive, coming out positive, flux at the bottom coming out positive. But if you look at the vector D, you have opposite direction. But that has got nothing to do with Gauss's law. Gauss's law is not a field theorem, it's a flux theorem. The Gauss's law says integral of D dot ds. Now, for every integral law, we have a corresponding differential law. I think you learned this from vector calculus. Vector calculus, you learn already. But let's see now. So we have here Gauss's law, integral of ds is equal to net Q enclosed by Gaussian forces. Net Q enclosed by Gaussian forces. So again, I have to emphasize that Q here is Q free, not sail Q free. Free means these charges on conductors, they can move. Very important. Because when it comes to analyzing problems with a dielectric, in the dielectric, like capacitor plate, you have two capacitor plates, you put a quick dielectric in between. The charges, the electric field from the charges on the conductor will polarize the dielectric, creating positive negative charges inside the dielectric. But when you apply Gauss's law, all charges which are not on conductors are ignored completely. So this is engineer's Gauss's law. But the physicist Gauss's law must take into account the charges on the dielectric. I'll explain to you later. I'll show how complicated the law becomes for physicists. Engineers make things very easier. Very convenient. I'll tell you afterwards. So, for every integral law, we say integral law. So if the charge density is rho, integral dV in a marginal case. So you can see you have a volume integral. This is Coulomb per meter cube. This is meter cube. dV Coulomb. This is Coulomb per meter square times meter square. So they agree. Both sides Coulomb. You can see. So Coulomb. So for every integral law, we have a differential law. Why? Because of math, but it's very convenient. If I give you the charge density, charge distribution, you can calculate what's the E, D, that is the E, or the method we will talk about, right? But another question is, if I give you the D or the E, what is the charge? But we know there's an integral law. So what we shall find is that according to divergence theorem, divergence of vector D is equal to O. This is scalar. This is scalar. D is a vector. So the dot product is scalar. So those of you who are not used to this, dive that D. So therefore, if I give you the D or the E, if I give you the D, okay, you can get the E. If I give you the E, so E, you can find the D. And from the D, you can get the rho using this law. So this is Gauss's law in differential form. This is Gauss's law in integral form. So you will see that every law has the integration and has a differential law and make life less easier. So let's look at it before we look at the example. So how do you get this integration, this integration? That's really easy. Okay. So we are going to, this is the handout that we have in integral form. We want to get the integral form. So consider a small cube of charges, okay, free charges from that conductor. So this vector D displacement connected with E, I've got three components, dx, dy, dx, dz. So over this surface here, I'll show you the next cube, I'll expand this over here. This is x, y, z axis, I have the set. Here this is dy. Then after delta y, this is dy plus delta dy. Similarly, dx and delta dx, similarly dz delta z. So that's my down here. The net in the y direction, the net flux coming out of the volume in the y direction is given by dy plus delta dy multiplied by delta x times delta z. This is the z. So this is outward flux positive. From the other surface, is dy times delta x delta z. It is negative because it's in negative. the other two components are added with delta dy times delta x delta z, plus delta dx delta y delta z, delta z delta x delta y should be equal to the total for that rows. So density was rho free multiplied by the volume delta x delta y delta z. In the limit delta x delta y delta z to 0 becomes the derivative divided by delta x delta y z. I get this one here. In the limit of the volume tends to 0. I get the result which I am looking for. But this is dimensions of vector. So therefore, Gauss's law in differential form, those of you can dot B, this is a scalar, D is a vector, the divergence is dot product is always scalar. So therefore, you can see now we are armed with Gauss's law. If I give you the charge distribution, calculate the field, using two methods. One, the long method, so the first one was symmetry, apply Gauss's law directly in the flux. Then, if you are given the field, now calculate the charge, delta density, you just take divergence. I showed in this particular example. Given the electric field given by x square y around ax, x y z around ay, minus 2xz around az, I can find out the charge density. I can take divergence of B, take divergence of this. Divergence is just here. Partial d dx by dx, component. D dy by dy, d dy by z. Partial means difference with respect to x, y z constant. So therefore, you know the answer is given by epsilon naught 2xy. Therefore, given a electric field, I can calculate what is the charge that's causing an electric field. By taking divergence, by taking the dot product. So just to remind you, where the dot product come from? This is the del operator, x, y, z for the system. Del dot product, ax dot ax 1, ax dot y 0, and 4. Okay? So therefore, we are able to calculate the charge density, okay, from the field. Normally, people give you the charge, you can kind of field, you can go backward. Okay? So let's now look at this good example. You can see we can go in the forward direction with an answer. We take the answer, we go in the backward direction, which we get the original answer is like this. If we don't, something wrong. Inside the charges, we have R less than A, the field down there, you can calculate. Outside of our charges, also the field, let's see. But we have to make sure that we apply Gauss's law correctly. Now, first region R less than A. R less than A, notice carefully, R less than A. I have to make sure that my Gaussian surface satisfies this quantity, R less than A. So this is R equal to A. My point P, where I want the field to be, R less than A must be inside the dot. Okay? So my Gaussian surface must always pass to the point where I want the field to be, nowhere else. Makes sense, right? You want to go to Ang-Mo-Kio, you go to a train to Ang-Mo-Kio, you don't go to Clementi, isn't it? Because sometimes people forget. They're too busy trying to memorize without understanding, that's why you get in trouble. There's no memorization here. You want to P, anywhere in the circle here, on this sphere here, R is not A. This is A. A is R. There is symmetry because the ball of charges in the sphere at the given distance R, always the same P. But of course, as you move from the center everywhere, the radius, the dr will point somewhere else, different direction, but the value on the given fixed R should be the same. That's not a symmetry. Like if, for example, you look at the ball, whether you look from this side or the other side or this side, you always see the same shape. Symmetry, spherical symmetry. So now, assuming we have focus, you have focused carefully. This is my Gaussian surface. Gaussian law says integral of DDS. Integral of DDS, let us enclose. So integral of DDS, yeah. DDS is the net charge enclosed by the Gaussian surface. Integral of d dot ds is equal to net charge enclosed by the surface S. Because d at the given point R is the same, therefore it is given by dr multiplied by 4 pi r squared, is here. Net charge enclosed by the Gaussian surface is rho naught multiplied by the volume of the green sphere, not the red sphere. The original sphere volume is 4/3 pi a cubed. But the Gaussian surface, the charge enclosed by the Gaussian surface is not everywhere, but only part of the charges is given by 4 pi r cubed, not a cube, 4 pi r cubed. Is that okay? 4/3 pi r cubed. So I simplify, I find out that dr is given by rho naught r upon 3, okay, by dr divided by 0. Now, the next stage now is for R greater than A, outside the world of charges, obviously my Gaussian surface is different. Green Gaussian surface here, my point P is outside, R greater than M is now outside. Now, on the left hand side, the same, dr multiplied by 4 pi r squared, surface area. Charge enclosed by Gaussian surface is not the same as before. Now it is the whole charge, rho naught 4/3 pi a cubed. We get the two answers different. Two answers are different. Has to be one. Now the next question comes in now. Why did I mean, Gaussian law says that. The question is, why did I ignore the charges outside here, outside the green arrow? Or put it another way, what would have happened to the problem if I had included those wrong charges? So if I had done that, you see what happens. If I included those charges in, the answer will be wrong because part of the law doesn't say that. But I know the charges outside, I get the correct answer because you can see why. Left hand side is the net charge enclosed, the net flux contributed by the charges inside the Gaussian surface, inside, which is in the green arrow here. Okay? But then you can ask me now, what happened to the charges outside? They also contribute flux. Yes, they contribute flux, they all cancel. See here. So these charges which are found outside the Gaussian surface for the first part of the problem do not contribute because of the following integral drawing. Yeah. So if, for example, I take a small element charge here, the point charge. This gives rise to flux. And so on. So the next question I ask now, this element of charge which I have ignored, okay, is contributing flux also. But how come I didn't take it inside there? I didn't take it inside there, you can see, look carefully. The amount of flux that goes in here from this charge here is negative, is coming out from there, which is positive. In other words, the net flux contributing by the charges outside the Gaussian surface, they cancel identically. Because they contribute going in negative, coming out positive. So by conservation of flux, it's as if something goes right through, coming here negative, coming out positive, the net effect is zero. So that is why the charges outside the Gaussian surface do not contribute. We do not care about them. We don't bother about them because they're outside the Gaussian. Is that okay with it? And you can look at the same picture now. Take any other point. Take any other point and repeat the picture. Repeat the thing again. You can see. Here coming out. Here going in. Cancel. Okay. So the charges that are found outside the Gaussian surface do not contribute. That's why we always ignore, leave them alone, leave them out. Okay, let me give another picture, simpler picture. I have a point charge of plus Q here, will give rise to, at the point P here, give you flux, electric field. Suppose I have a charge in the vicinity of, so my Gaussian surface is here. Suppose I have a charge of, say, Q here, another Q2 here, or Q, whatever, Q. So this is not taken into account because the Gaussian surface doesn't include Q2, this is Q. Okay? So why? Because you can see this gives rise to flux. Whatever comes in must come out. So the net flux contributed by this to that Gaussian surface is zero because what goes in negative but come out positive. Cancel. So that is why the reason why when you apply Gauss's law, when you draw a Gaussian surface passes through the point where you want the field to be. Any charges from outside the surface is completely ignored because they contribute zero flux to the Gaussian surface. Is that okay with it? This one will give you. This one here, this Gaussian surface. Here, negative, coming out positive. Of course, there is flux here, but we don't care. We are asking at this point P, of a P here. We are looking here at P. We don't care about the rest. Right? We want to fill the point P, we don't care about the rest. My Gaussian surface going to here, not there. Of course, if I pull my Gaussian surface now, I change the problem. My Gaussian surface now is including both. Then I cannot ignore it. Definitely, right? Of course, then there is no symmetry. We can always apply Gauss's law, but whether you can get the answer very quickly is a different issue. Playing 4 digits, you can always play 4 digits for number and play. So whether you win, that's a different story. Okay? So now we have taken integral form Gauss's law, integral form from charge, get the field. Now question is, if you take the field now, we apply the differential law, can we get the charge density? That brings up equal to rho. Let's see. Of course we shall need, but of course, since the body has a symmetry, we have to use the operator for divergence in spherical coordinate. In spherical coordinate system, my ball of charge has got symmetry, so therefore d by d theta is 0. Anywhere you look, 0. D by d phi also 0, only the to do this, you substitute in the operator. When you do it, divergence of this given this, you work it out slowly for the two ranges. I leave it to you to do. You find that for R less than A, you get rho naught, as you expect. For R greater than A, you get 0. Is that true? Look at the picture again. Concentrate. So the first one, we get already. For R greater than A, take divergence. R greater than A. You're looking for the region R greater than A. R greater than A at this point here. What is the charge there? There's no charge there. The charge is inside, not there. That's what we want to do. At the point B, when you take divergence, you get rho naught. It's a density. At the point P, when it's outside Gaussian surface, you can see when it's free space, there's no charge there. And you do the calculation, take divergence of this, you can see. So therefore the law is correct. You either way is correct. There is no free charge for R greater than A. We know that. The ball of charge stops at A. Outside is nothing. Okay, so I put a note here, which I will explain already. About the free charges. The free charges are the charges that are found on the conductor, not on the dielectric. And I will show you how engineers make life always easier. Physicists make life more complicated. Unnecessarily complicated. Such issues. So before we look at the new topic of potentials and things, let me just show you how the engineers are to go make life much simpler. That's why you read a book on physics, you find a lot of complications. But the physicists of course started with the thing first. So you can see physicists Gauss's law. I call it physicists Gauss's law. Physicists like to work E. The integral E dot ds, same thing, on surface, is given by net charge Q upon epsilon naught. Epsilon naught, whether you have dielectric or not, always epsilon naught. So therefore, what is this Q? Actually, this Q is physicist Q, Q free plus Q polarization. So this is the physicist Gauss's law. He needs to find out information on the charge and dielectric. Sometimes complicated, you cannot do because you're looking for E, how can you find two things? Very difficult, not so easy. So the Gauss's law is, I'm telling you, we do not work with polarization charges. Engineer Gauss's law. Integral dds is equal to Q free. That's it. That's how we did what. But now the question is, when engineers formulate a law like this, he will have to define Q polarization in terms of electric field. So engineers will use Q polarization through some definition of polarization charges, electric field, and something called chi, not the chicken, chi. So the electric field E polarization is chi times E. Polarization vector is proportional to E. Okay, and later on we find out that chi is same as epsilon r minus 1 times epsilon r. So very complicated, unnecessarily complicated. So therefore you can see the engineer Gauss's law say no. So if you want to use the physics Gauss's law, you will have to find the polarization vector. You have to be given this, find E, and also find all kinds of things. So this is not necessary. So we can say we feel that this engineer's law is Q-free. All charges not on conductors ignore. All charges, all electric charges found on non-conductors should be chucked them away, throw away, discard, don't bother, ignore. So you can see that unless you use Gauss's law, you have problem with the conductor. Power paid capacitor, V naught, 0 volt, charged up. Those are charges on the conductor. Q. You have minus Q on the other conductor. So Gauss's law, we say, okay, we can do a Gaussian surface, find the D, find E, and that's it. But in the case of the physics Gauss's law, you have, if a dielectric here, you have a problem. You have a dielectric here, epsilon r, you have a problem because in the dielectric, negative induces negative positive. And on the dielectric, positive, negative, positive, negative, positive, negative, positive, and so on inside the material. So when you apply the physicist Gauss's law, you got to know what those charges are. You can find them later, but what for? Why do you want to bother? So engineer Gauss's law says, forget about charges in dielectric, find a Q on the conductor, full stop. That's it. So to amplify this, those of you interested, you can look at books in physics, you will see how they formulated Gauss's law. They seem to like epsilon naught. We have this. But you can see how we engineers do. They calculate D, and they get E equal to D over epsilon naught epsilon R. The physicist Gauss's law got no epsilon R. Epsilon R hidden somewhere here. Hidden somewhere here. So I think I won't amplify anymore. You need to go and have a look to satisfy yourself. That's why we stick engineer Gauss's law. We are not interested in polarization charges, we are interested only in charges on the conductor. Okay? Now we go and look at, you can see so far we have got a vector, E, force, vector, electric field, vector. Now scalar, flux, integral ds, flux, scalar. But now we also can find, you can see when you have vector, you have a lot of problems about direction. But now, we shall see now, electric field can be connected with scalar through the concept of work done, potential, voltage. So what we shall see very soon is that if I have a voltage V as a function of x, y, z given to me, if I take the gradient, grad, I get E, just like E. Vector, scalar, when you take the grad gradient right is a vector. This one you learn the calculus in your vector analysis. Okay. So we can link a vector here with the grad of a scalar. And what you will see, I just draw a bit. We shall see the integral of E dot dl, integral of E dot dl, vector, scalar, okay, will be linked with the voltage. Okay, later we shall see some limits there, we'll take some limits, so we shall see the integral is a minus 1 to 2, is V to 1. Scalar, vector becomes scalar. So therefore, what again we can see now is, if I give you a field vector in a given region, you can find what's the potential difference between 2 points 1 and 2. But now if I give you the distribution of voltage in this little room, you can determine what the field, electric field distribution is. So for every integral law, there's a differential law. Now we proceed to look at the potential, the scalar. And the scalar involves the concept of work done. Work done. Work done in the scientific sense. Work done can be force is a vector, multiplied by dl, element of path, and gives you the work done. For example, if I walk up the stairs, gravity is pulling me down, my weight is mg, the height of the stairs down there is h, the work done is mgh. You know that already. Okay. So if I walk down again, I lose potential energy. So therefore, I go from bottom to top come to bottom, the same point, zero change. Zero work done. Okay. But the concept of work done is always force times distance, But the force, okay, F dot dl again, dot dl, which you have done in your maths. Here the force is F. Vector, element dl. Therefore, this is theta. It is F cos theta times omega. Now you know already. Okay. So the person who skates on an ice, thin layer of ice, he stands vertically, he does zero work. If the surface of this ice rink is horizontal, as it slides, he's doing zero work. No work done. His gravity is down. His movement 90 degrees, F dot dl, F cos 90 degrees 0, no work is done. So slides. Okay, so let's now go look at this concept of potential. But we have already encountered force. So you get the force and work done, work energy. Okay. So I have two charges, Q1 and Q2, as before. You can see now if I hold Q1 here, positive, Q2 positive, I let go, you push towards, away from Q1. If I hold Q2, I let Q1 off, free, it will go the other way. You want to do it. So therefore, you can see, in order for me to, in that sense, to prevent the charges from going somewhere else, I have to hold them. In other words, when I hold them like a spring, I'm doing work. As an external agent, I'm doing work on them. If I let go, you fire. So, let's look at the electric field here. 2 point A, B, element dl. I take the charge of first Q and I move a distance of dl, delta L. Okay. But now remember, charge is positive, when I push it in the electric field, there will be some repulsion. Therefore, I have to do work to prevent it from repelling, so I have to push it. So this is I'm doing negative, I'm doing work, external work. That is why you have the minus there. So the work done against the electric field, preventing it from flying off, I have to hold it, and I push it in the field, meaning I'm contributing, doing external work, okay, minus here, external agent. If I do external work, minus Q times force, the E down here, force. If I let go, the field is doing work on the charge. The field is pushing positive work. But by definition, you shall see, the work done per unit charge by an external agent is defined as the potential. In this case here, the work done moving a charge of Q, this is dl, is QE dot dl. Why? Because field is force per unit charge. The charge is Q, therefore the force F is Q times E. Dot dl means around element dl, cosine theta there. Therefore the work done to move the charge from A to B, integral A to B minus QE dot dl minus QE dot dl. Now this seems a bit trivial, but I have to highlight to you pitfalls. So people just simply do memorize the wrong thing, and get all wrong. Similarly, I can substitute there, you can see. So when 90 degrees, substitute. So the work done is given by minus QE dot dl of A to B. So the potential difference is defined as the work done per unit charge. W on Q, Q is plus 1 as before. So the command is done here. So therefore you can see. B, and you take the charge of go from A to B, do the work done. This means the potential of B respect to A, VB minus VA, potential of B minus VA. Like gravity, I go on top, bottom the difference. This is minus integral A to B, E dot dl. So the potential difference is joule per coulomb. Work done is joule per coulomb per unit charge, or more commonly, of course, it's volt. Joule is ampere volts second, ampere and volt second, divided by coulomb ampere second, cancel, therefore it is volts. So therefore the potential difference is joule per coulomb or more common volts. You never say this voltage is so many joules per coulomb. This is what you're talking about. The volts. Okay? Now, I want you to look carefully. Potential of B respect to A is minus integral A to B minus E dot dl. Not B to A. This I will amplify very soon. So let's look at the case now. Potential at a point charge, from a point charge Q. This is point charge Q. Okay. At the point P, I have a unit test charge. Again, test charge QP is 1. I'm going to hold it there, positive, in order to prevent it from flying off. Okay, you can see I have to hold it slowly, which will be work done. So the work done against it will be equal to VBA is minus integral A to B, E dot A to R B, actually the R of the here. Now, when you do this kind of integral, E dot dl, you always keep the dr positive. You always keep the dr positive vector. That if the dr is along y, then the dy is ay dy. Is along x, is ax dx. irrespective of how you move it. So the question is, I get the right expression by putting the limits, putting the correct limits, then you're okay. In this case here, you can see, going from A to B, going from B to A, I take the charge, it says charge here, I push it against the attraction forces, because it's being repelled, I push it towards A. Push it towards A, work done by me is minus integral ER dr, or E dot dr, okay, from A to B. So, ER is, we know already, Q times 1 over 4 pi epsilon R squared, integral of 1 over R squared minus 1 R squared, 1 over R. Okay, 1 over R here. AB. But what we notice is that for a point charge Q, the electric field varies of 1 over R squared at the point P, and the potential voltage 1 over R, because I have done an integration. When I integrate 1 over R squared, it becomes 1 over R. In other words, the potential drop slower than the field, much slower than the field. Now, since we are dealing with electrostatic field, the shape of the path doesn't matter. If I go from A to B, or I go from A to B like this, or like this, or go like this, come back somewhere else, the answer is always the same. The answer is the same. Okay, the only difference is that the only component is that the points are same. So this is, so now if you can see now, if I integrate from A to B, I get an answer. I integrate from B to A, I get another answer. If I add them together, I get 0. Just like I woke up MGH, I come down minus MGH, also the answer is 0. So this is a characteristic in general of a electrostatic field, a non-varying, time-varying field. If I go from A to B, E dot dr, I get an answer, potential difference between A and B. Whatever be the path, I go from B to A, I get an answer which is calculated. But you can see what. In one case, you are going this way, say positive, come back negative work. So I think you're taking 0. See, go this way, come back. So the point A and B coincide as if coincide in 0. So no work done around the closed path. But this thing you already encountered in your circuit theory, Kirchhoff voltage law. In your resistor EMF, across a closed loop, summation of voltage 0. You equate the EMF to the voltage drop, or when you add everything on the left, the EMF minus voltage drop gives you 0. Why? Because you're going on the loop. You're taking the mesh law on the loop. This is Kirchhoff voltage law. Okay? Familiar KVL. Now, what happens if the point B, the second point is at infinity? A at infinity. You can see 1 over infinity is 0. Answer is given by potential AB, which is given with respect to infinity, which is given by Q 4 pi epsilon R B. But here, notice, this is only true for EM fields, electric field which do not change with time. D by dt equal to 0. So the question is, how come this happened like this? Why? Can I give a counter example to show that this must be so, this cannot be so? Why? So the integral E dot dr for electrostatic field is 0. But when the field changes with time, it is not 0. Question why? Can I give an example? Some of you have done machine or something, a magnet here, north south. magnetic field here, magnetic field, magnetic flux, whatever you want. So this Mr. Faraday, Michael Faraday, what he did was with the experiment, he take a loop, this, put some meter on there, and sweep it across there, move it very fast. So now we have motion now. The loop is moving with time. So what he finds is that there is a voltage going there, EMF, current going there. So these two points are very close together. Therefore, integral of E dot dl is not zero. It's not zero because you observe there is a magnetic field, there is a voltage on there. So the question is, if E dot dl is not zero, there is something wrong. No, there is nothing wrong. If I walk up the stairs, you see gravity up there, mgh, I come down minus mgh, so sum of the work done is zero. So in the case of Faraday, he takes the loop and he pushes it across the magnetic field. He found out that there is a voltage there across the ends of the loop. The reason is that he has provided extra energy by moving the loop across the magnetic field. The energy comes from him and moving it. And he has to move it to create d by dt, not zero. If d by d is zero, the loop just remains the same as nothing happens. Right? If there's no time variation, the loop just like this, nothing happens. You're back to something zero. So you move it like that, it means you're changing with time, because the time element there, he has to add some energy from himself in his hand. So therefore, E dot dl for time magnetic field is not zero. It cannot be zero. If it was zero, there would be no light, no electricity, no PUB. In a PUB station, the alternator is turning, the conductor is moving across magnetic field to generate power, voltage and current. And then you can use the thing to power your house and on or whatever it is. If E dot dl was zero, nothing come out. The whole world will be in the Stone Age, still living in caves, nothing happens. Let's look at the last bit of this. So as I mentioned to you, integral E dot dl, okay, when you take A tend to infinity, the limit A goes to infinity, and this is the infinity. This is sometimes people cause some confusion. They say, oh, the potential at this point is so many volts. Actually, this statement is not correct. Potential must always have a reference. It didn't say. It said the potential at this point, with respect to the infinity, or with respect to the ground, is so much. There's always a reference. Of course, he assumes that you know. Okay. So we say the voltage of this is 20 volts, respect the ground. But voltage by itself cannot exist in the electric. Now last bit now, I told you about how to calculate integral E dot dl. You always take dl as positive, just put the limits there. Give an example quickly. This problem given to you. I give you electric field E is minus AX, Y minus AY X. AX and AY are unit vectors of X and Y. Calculate the voltage VCA, VC minus A, VC minus VA, using two paths. First one along ABC, okay, the other one is along AC. Okay, as we said before, this is the electrostatic field, no time here, therefore we must get the answer the same. No time here, we see. Let's see first one. Path ABC consists of this path and this path. DL is simply equal to AX dx, AY dy, all is positive. We know EDF, E, dot product, again. Again, equal A to B, When I go from A to B, notice X doesn't change, therefore dx is 0. Dy changes from 2 to 6. Okay? When I go along along the next path, BC, I go along the path BC, dy doesn't change, therefore dy is 0. Along the path BC, y is equal to 6. I substitute, I get 10 equals. So I found out that the potential of C respect to A is higher than B. Now I go directly from path AC, from A to C. Now, geometry, coordinate geometry is a line. Y is, the path is given by y is equal to 2x minus 2, y is equal to mx plus c. Dy is equal to twice dx, y is equal to mx, I gave 2 points. Geometry, okay, you can remember coordinate geometry. Y minus y2 over x minus x2 is y2 minus y1 over x2 minus x1. You learn in your coordinate geometry, trigonometry. Substitute. You know dx, you know dy, substitute. Everything is okay, 20 volts. So you get the same answer. If you have obtained minus 20, you are wrong already. Something has happened, like copper. So the key in evaluating this integral correctly, first always take the path positive and let the limits take care of themselves. But of course, just remember, potential of C respect to VCA means potential VC minus VA is minus integral A to C. Okay? Now before we stop, give me 5 seconds just to show you how we have to be very careful what we do. Everything we do must be done with justification, without memorizing the wrong thing. So we saw delta V by delta L is minus the E factor from left to right. So we found out that delta V is minus integral dl. So I integrate now from A to B, integrate from A to B, so you can see this is VBA. So VBA, and so I do this one here, integrate both sides, A to B. This comes from the integration of the differential law. So dV by dl is minus E. We are going to get from A to B, I integrate both sides the same way. Okay, so we shall stop here. Please come back at 8 o'clock. Or earlier, not after 8. We'll start with